All right, guys. So welcome to another lecture in 102. And today we are going to complete or finish the thermodynamics module over here. So this is going to be the last material that we are going to discuss under the topic of thermodynamics. All right. So, wow, it's been like, I don't know, 3 weeks already. Yeah. So this is closing the third week and we are completing this thermodynamic stuff over here. All right. So this is going to be the sign that we are going to, approaching the first exam very soon, but that's up to you, right? It could be anytime. It doesn't have to be right after. I mean, it doesn't have to be next week, right? It could be any week. All right. So after today's lecture has ended and everything, I will put like there's a poll so you guys can check out the vote and then we'll come up with the good time that we can. I think I'm going to have only a single exam date among two sections. All right. So that's just easier to arrange. And then I think everyone can just, do the exam at the same time. The format of the exam is going to be take home exam. And just from the voice from the other sections, they said that it probably better to start the exam during the afternoon time. So it's mean I used to release the exam like 8 o'clock in the morning, and then you have 12 hours to complete. So you just hand in your work at 2 p.m., 8 p.m. However, they said like, okay, John, why don't you start at noon and runs until the midnight? So that sounds good. I mean, it's fine by me. And I think by thinking about it, I think you guys seem to maybe work sort of like toward late during the day than just earlier. I guess you guys sort of like still young, and then you seem to like, I don't know, spend time at night more than during the day, I guess. I don't know. All right, but anyway, we can comment or just make the final decisions soon. Okay, after the poll is up, and then you guys can just come up with the agreement. Okay, sounds good. All right, but at least the good thing about the format of the exam is you don't need to memorize anything. You don't have to, it's like open book, open web, open everything. All right, all you need to do is just make sure that you stick with the rule. Just sort of like it's is definitely going to be individual work. So you guys not supposed to share your answers, solutions, or try to work the exam in a group. That will be fine. Okay, sounds fair enough, I guess. All right, so that's it. So we can decide that later. So I'm expecting that the exam should sort of arrive maybe 2 weeks from now. So yeah, so you guys have time to study and look through the homeworks and exercises and everything. Okay, sounds fun. Okay, all right. So let's having more fun today about thermodynamics. Um, what I'm trying to do here is we have one more exercise to go through, and I'm planning to have this one as a review of everything that we have done. Okay, I mean everything means first law of thermodynamics and the applications in heat engine. So what I'm going to show you here is I'm going to go through this problem in detail. So you'll have a chance to take a look at this one more time and sort of like see the whole pictures, okay, once again. Okay, sounds fun? All right, let's take a look at this. What is the thermal efficiency? The question is just so simple. It's simple in the sense that it's so short. Hey, give me the efficiency of the engine, okay? That's described by the following PV diagram, and it has n moles of gas to be the working substance in this engine, and it's assumed to be monatomic, ideal gas. So go ahead. All right. So because if we would like to just answer this question, that is sort of like a short version to get to the final answer. But as I said, I would like to use this one to showcase how the first law of thermodynamics works. So I'm going to go through each segment one at a time and see how it goes. All right. And I hope things will get faster and faster once, familiar with this kind of problem. Guys, ready? Yeah. Okay.
Okay.
1 to 2. It's constant volume. So no work done, definitely. So the first law of thermodynamics, we read the change in the internal energy is going to be the heat flow. The W term is gone. Very nice. And because we know it's a monatomic ideal gas, U is 3/2 nRT. So the delta U is going to be 3/2 nR delta T. Cool. All right. Now, because you're going from 1 to 2, so it's going to be 3/2 nR T final, which is T at 2 minus T initial is going to be T at 1. Nice. All right. However, what you're seeing over here is, if you recognize briefly, we mentioned this because it's the heat is written in terms of the N, the constant, and the change in the temperature. You can write this one as a N C sub V delta T. Okay, remember this one?
Okay.
All right. So that means in the constant volume process, you can jump right into the heat calculation using N C sub V delta T. And for monatomic gas, C sub V is 3/2 R. So that's what it is. Okay. Now, keep going. So what I can write over here is, well, Ajahn, we don't know the information about the temperature, but that's all right. We have PV equal to nRT. So that means I can turn nRT into the product between the pressure and volume all the time. Okay. So that means what I'm going to get is going to be 3/2. Just leave it there, just a constant in the front. And I can say nRT. There you go. Okay, let me highlight for you guys. nRT over here, that is going to be PV. So it's going to be P2V2, and nRT1 is going to be P1V1. Looks good. All right. And from here, then you can just read from the scale on the PV diagram. P2V2 is 2P naught and V naught. So it's going to be 3/2 2P naught V naught. Cool. And at the position 1, you can see that it's P naught with the V naught. So it's going to be, subtract out the V naught, P naught. There you go. All right. And that is it, guys. So what you get is 3/2 P naught V naught. You're done. That's it.
Okay.
2 to 2. Looks good. Sort of like, is this a good way of going through this? I hope it works. All right. And what you can see from here is the sign will be taken care of automatically as long as you take the delta to be, in the proper order of subtraction. So over here, you get the final result to be a positive number. So that means if you look at this value of this one is a heat. So it means there's a heat flow in. It's a positive heat. Okay. And because it's equal to the delta U, so it means the internal energy is changing in the positive direction. So it means the temperature is supposed to be up. And once again, just remind you what we discussed many times, that every time you see PV diagram, imagine that you have isothermal line. All right, 3, 2, and 4 might not be on the same isotherm. So I just try to draw 2. Okay, 1 for each point, but they could be on the same line. Who knows? All right, but let's assume that yeah, it could be not, but in general, from the look of this one, it is. All right. But anyway, okay, just writing without knowing it first. Okay, so what you have over here is, by analyzing this line 1 to 2, yeah, it's up. Jumping from lower lying isotherm to a higher lying isotherm, so it means you're going up in temperature. So that's make completely perfect sense. Completely perfect sense. Yeah. All right. Cool. Any questions so far? All right. So what I can do is I can actually sort of draw an arrow saying that, hey, guys, there is a heat flow in 1, 2 right there. Let me put the subscript 1, 2 just to signify that I am talking about the 1, 2 segment over here. Cool. All right, keep going. All right, let's talk about 2 to 3. Okay, so during this process now is a constant pressure process, isobaric process. So we sort of remember vaguely like that this process will contain all 3 terms. So all 3 terms in the first law of thermodynamics are non-zero. Okay. All right, so let's go through with this. So let's attack the easiest one, the work. Work is of course, just remind you, is the integral of PdV. Yeah, and it's going to be the area under the curve. Okay, oh, there's a question comes in. Okay, if internal energy increases, the temperature has to always increases, right? Yes, exactly right. Very good. Okay, because we already agreed that for the monatomic gas, temperature tells you the level of the energy. So if you have the change of the internal energy, that always means temperature must be changing along with it. Yes, that is good. Okay. All right. Come back to our business over here. So the work done is the area under the curve. So going from 2 to 3, the area that we are talking about is just going to be this area down here. Let me highlight for you guys. Yeah. It's just a rectangle over here. So it's the width times the height. The width is going to be V naught. The height is going to be 2 P naught. Cool with that? All right, guys. So that's good. So it's just the area under the curve. All right. And don't forget to be going from left to right. So it's an expansion. So if I write this to be area equal to A, the area underneath, you know it's going to be the positive A of work that's the gas is doing right now, because gas is expanding. So gas performing works itself. So the work done by the gas is positive. Cool. Already. Nice. Equal to 2 P naught V naught. All right. First parameter is down. Move on to the next. What else do you know? Well, Adan, of course, the next one that's kind of like okay to calculate is the U, because we have the formula. So let's go through the U. The delta U is 3/2 NR delta T all the time. Okay, so that means it's going to be 3/2 NR T at 3 minus T at 2. Very good. And we do the same tricks just like before. nRT equal to P times V. So you can just say this is going to be 3/2 P3 V3 minus P2 V2. Yeah, cool. Okay.
Okay.
All right. So with that, then read the graph at point number 3. The pressure is 2 P naught, volume is 2 P naught. So that will give you 4 P naught V naught. Subtract what is going on at point number 2. You read 2 P naught, 1 V naught. So it's going to be 2 P naught V naught right there. Okay. Very nice. And that, all right, you've got 2 P naught V naught in the bracket, 2 cancel in the front. So you are left with just, let me sort of make sure that I put the sign so it's obvious. 3 P naught V naught, which is good. All right.
Okay.
The reason I'm saying it's good because once again, the delta U is positive. So it means temperature is rising during this segment, which makes sense because going from 2 to 3, you see, you're jumping from 2 all the way to 3. So it means you're going up in you're going up in isotherm again. You're jumping from a lower line to a higher line isotherm. So temperature is supposed to be rising. So you're doing positive change in the delta U. Cool. All right then. Whoa, what did it do? Oh, no. Okay, very good. Woo. Alrighty. All right, so let me erase this. No, I don't need to erase this. It's going to be too hard to erase now, but all right, that's okay. I hope it's not too dirty. I thought I'm just going to undo this, but I already missed that chance. Okay. All right, so now we arrived at the heat now, the last one. So once you know those W and the delta U, now you are ready to calculate the Q. From the first law of thermodynamics, Q is just a delta U plus W. Yeah, I just moved the negative W to the other side. And now you just take the delta U and W that you just got, add it here, and you are done. So you're going to have 2 and 3. So that's plus 5 P naught V naught. That's it, guys.
Okay.
Isn't that cool? Right. And once again, if you remember vaguely about that, it's kind of like, sort of like feel that you also have another formula for the heat during the constant pressure process. And that is, if you remember, 5/2 NR delta T. You remember that? Yeah. Okay. And this, you call it NC sub P delta T. See? So actually, if you really care about just the heat and you don't want to, I mean, because you sort of understand everything, you can just dive into Q calculation right away. And then you just say, okay, I know that the heat during this process is going to be 5 half NR delta T. Okay. And you have already calculated that the NR delta T is just this bracket over here. You guys with me? Okay. And that gives you 2. So that means once you substitute that NR delta T, which is PV minus PV, then you're going to get, okay, let me write it on the side here. There you go, 5 half with the bracket, 5, I'm sorry, 2, sorry, 2 P naught, V naught. Got that one? Okay, let me highlight that one so you won't get confused. I got it from here. Same thing, these two are the same. All right, and once again, 2 cancel. So you end up with the same result, 5 P naught, V naught. Cool.
Okay.
Yeah. Okay, that's a question. You never knew U of constant pressure is also 3 half nRT. Why is that the case? Come again? Kind of confused. What do you mean by never knew? U of constant pressure. Okay. I think I got it. So because internal temperature, internal energy depends only on temperature. So in terms of the gas, it doesn't matter. You bring the gas from one point to another point using any process. Does that make sense? Right? Because what I'm saying over here is you never knew that U of constant pressure. To me, I don't need to know it's a constant pressure process or not, because as long as you're starting from point 2 to point 3, the delta U is always 3 half NR delta T. Delta U is always 3 half NR T at 3 minus T at 2. You don't need to even specify what process you are working on. Does that make sense? It's path independence parameter. So I can use with yes, exactly right. Yeah, because that is the property of the gas. It's a property of an ideal gas. So in an ideal gas, we had this relationship. U is always 3 half nRT all the time. That's it for a monatomic ideal gas. This is always the case. So when you want to find the change, so it's just 3 half NR delta T. Don't need to specify any path at all.
Okay.
Okay, very good. All right. I think that's a very good question. And I think you have to get this thing sort of stuck in your sort of like the underlying or infrastructure of this first law of thermodynamics. Otherwise, then if you sort of like have no confidence using this formula, things would get very, very chaotic, because all 3 terms in the first law of thermodynamics will be like path dependent. And you sort of like, you have to worry about this, about that all the time. But the good thing about this one is Q and W are the 2. Oh, keep hitting this back button. Q and W are the 2 that is path dependent. And you left the delta U to be the good guy here. Like, a very good guy is that, okay, it's easy to calculate. It's always, stick with the equation. Yeah, 3 half nRT. Yes. All right, good. All right, so this one, just to review what we had last time about calculating the heat during the constant volume and constant pressure process. All right, cool, that's done. So just to put this result into the curve as well, we're using the green color. So what we are looking at over here is you have positive heat during this process. So you're going from 2 to 3, you add here Q to 3. There is a heat flow into the system. Okay, cool. And it looks getting, sort of, let me erase them all and rewrite it for you guys. It's getting bad. All right. Okay, that's cleaner. Okay, let me write here. So that's Q12. Oh, what is going on today? Something is wrong with my hand. Okay, here we go. And this is Q to 3. Here we go. Already. Very nice. Okay, so there's a question. If there's no path dependence, then can we just calculate for the whole cycle? Calculate what? So, oh, the U. Oh, okay. So, yeah. If the question asks you the U for the whole cycle, the answer will be just say 0, because the cycle will always cycle everything back to the original position, correct? However, during that cycle, like here, 1 to 2, you might have positive delta U, 2 to 3, okay, you have another delta U, but then 3 to 4, you can expect the delta U will be negative because now you have to drop down in temperature. And 4 to 1, another delta U that is negative to bring everything back to 0 summation. Does that make sense? So it depends on the question. If the question asks you, just like last time, you say, hey, what is the delta U for the whole cycle? You can just say 0 because you arrive back at the starting point. So is that the right answer? Yeah. All right. So what I'm saying is you still need to calculate for each segment if you really want to look into detail what is going on for each segment, right? But by knowing in the back of your brain all the time that, okay, the sum must be 0 once you're done with all 4 segments here. All right, you will see. They have to. All right, guys, try 3 to 4. Now things will get faster because now you're sort of familiar now. But Ajahn, that's once again constant volume process. You won't get any W, and you can jump right ahead into the Q or the delta U. They are the same, and it's going to be 3/2 N or delta T again, and it's going to be 3/2 N or T at 4 minus T at 3, and it's going to be 3/2 P4 V4 minus P3 V3. Yes. Yeah.
Okay.
Fast. Quick. No problem. And all you need to do is just read off from the scales now. What happened at point number 4? You just have 2 V naught, 1 P naught. That's good. Okay. And what happened at number 3? You say that's 2 P naught, 2 P naught, 2 V naught. So that's good. So you just take the difference between the two. And what I can see is at 4, you get 2 P naught V naught. At 3, you get 4. So the difference is negative 2. So it's going to be 3/2 negative 2 P naught V naught. With me, guys? Cool. Don't forget the negative sign, okay, because that's final minus initial all the time. So the 2 cancel. So what you get at the end is going to be negative 3 P naught V naught as expected, right?
Okay.
Because we're expecting that going from 3 to 4, you are dropping down in temperature because you're jumping from a higher line isotherm to a lower line isotherm. So delta U is supposed to be negative, and that's what you expected over here. And it's the same as the heat because we don't have any work done during this process. So what I can conclude over here is you're going to have heat flowing out during this 3/4 segment. Okay.
Okay.
So good. I don't know, so good or not, but it seems like, I mean, once you get that first law of thermodynamics in your hands and then you carefully calculating each term properly, that's no problem. It's just annoying that there's so many tiny little things that you have to take into account all the time. Grab some from the equation of states. In the case of the idle gas, you have another equation for the U. You have to know the definition of the work done, on and on. But that's pretty much it. Okay? Once you know each component, then everything else it's just like cooking. Yeah. You need this ingredients, that ingredients, and you have to know what to pick. All right, guys. Last one. Okay, let me give another color over here. Let's do orange. Going forward back to 1. Now it's gonna be quick because but John, what you can do, you can just say Q is just 5/2 NR delta T right away if you want. You guys with me? Okay, because I mean, you know, if you want to go straightforward way, you just do delta U, 3/2 NR delta T, and then you do W, which is P delta V. Once you add them up, you get 5/2 factor. You sort of, all right, we have seen this so many times. And if you really want to figure out just the work done, it's just going to be the area underneath, and that's going to be this area right here. And you can expect that this work done is going to be a negative work done by the system because you are compressing the gas down. Cool. Okay, that's no big deal. However, for us at this point, we are interested in the the heat. So we can jump right ahead into the final result. It's going to be 5/2 NR T final, T at 1, T initial, T at 4. And you use the same trick one more time. It's going to be nRT equal to PV. So it's going to be P1V1 minus P4V4. Okay, and that is it. So you just read off from the curve again and from the graph again. So it's just P1 at position 1 is P naught V naught. At position 4, it's P naught 2 V naught. So whatever you have in the bracket is going to be negative P naught V naught. You guys with me? Make sure that you take into account the negative sign. Cool. I mean, once again, it's just the area of this block right here. Width times height. Width times height. There you go. Okay, P naught V naught, but it's negative. All right, guys, that's it. So what I'm having over here is, okay, let me rewrite, make it nice. 5/2 P naught V naught as expected. Okay, heat is flowing out. Q41. And you pretty much get every information that you can think of this diagram right here. Okay, now can you answer what is going to be the efficiency of this engine now? Sure hope so.
Okay.
Because you have everything in your hand right now, right? So look at this. So what we have over here is now you know each segment there is a heat flow in and heat flow out. The reason I want to emphasize on this problem, we remember we did this last time, yeah? But last time we have 3 segments, okay? And the key concepts that we try to sort of make sure that you understand when you apply this one is, even though we're going to, oops, sorry, even though we use, okay, let me add extra page here. Even though we use the simple diagram to represent the heat engine, but this is what happened in reality, okay, that you have a couple of segments that you have to take care of. And the main diagram goes like this. You have heat flow in, you call Q hot. You have heat going out, you call Q cold. And you said whatever left over, that's your work done, right? According to the first law of thermodynamics or conservation of energy. Now, what you have over here is, now you have a diagram and you have a cycle over here. Okay, and as you can see, you have 2 parts that heat's flowing in. Q12 is in, Q24, so 23 is in. These 2 has to add it into the Q hot. You guys with me now? Because this is the part of the heat that is flowing into the system. So what I'm trying to say over here is this is going to be Q12. I just take the absolutes because I know it's flowing in. So I just take just the number plus Q23. Remember, guys, that we just, okay, we know the direction. So for this particular diagram, I don't need the sign anymore. Cool. And same thing goes with the other side of this one. Q34 heat's leaving and Q41 heat is also leaving. Okay, let me change the color here just to make everything coincide. There you go. And those 2 will be the heats that you pretty much release to the environment or whatever. So that's what it is. So the Q cold down here is going to be 2 parts. That's it. You are done.
Okay.
Cool. And plus, what we really want to take a look at this is, okay, let me work these numbers out so you guys can see everything sort of like 100% in clarity over here. let's go back and grab the result. Q12, the red is right here, 3/2 P naught V naught. And the green is 3 P naught V naught. Okay, so it's 3/2 P naught V naught. Oh, am I right? Yeah, plus 3 P naught V naught. So that is your Q hot. That is the heat flowing in. Okay, cool. All right, and now look at the bottom part over here. So what you're getting over here is Q34 and Q41. It's 3 P naught V naught and 5/2 P naught V naught. I just gonna grab the number because I know this amount is moving out from the system. All right, so 3 plus 5/2. So what I'm getting is going to be what? 11/2, 11.5 P naught V naught. So that's what I'm getting, 11/2 P naught V naught. Over here, let me work this number out. I mean, too much color over here now. Okay, was that 9.5 P naught V naught? Here we go. All right, and down here is 11.5. Okay, there you go. All right, guys, you guys with me? I think number is incorrect. Something is wrong here. How come in is more than out? What happened? I must have made a mistake somewhere here. Guys, help me. Whoa. What did I do wrong? Oh, no, this is right. Which portion is incorrect? 3/2 P naught V naught. Looks good. The green, it's gonna be 5/2. Oh, it's 5. Sorry. Yeah. Sorry. Yeah, I circled the wrong one, guys. Sorry. I circled just the delta U. All right, you guys. Thank you. There you go. That's what we want. That's not what we want. The one on the top, that's not what we want. Okay, let me sort of like, okay. All right, here we go. That looks even worse. All right, but anyway. Okay, so 5 P naught V naught, guys. Sorry for the second segment there. Okay, I found it. Sorry. 5. Here we go. There, and that will be 13 instead of 9. That's better. There. All right. Looks good. 13. All right. Very good. Thank you. Oh, all right. Perfect. All right. Okay. So what we have over here is now the incoming heat is 13.5. Outgoing heat is 11.5. So your W is going to be just the difference between the two, right, you guys? So what is it? 13 minus 11 divided by 2. That's just P naught V naught. Okay.
Okay.
Does that make sense to you? Well, yeah, because remember, every time that we have a cyclic process, and when you go clockwise direction, what is the work done by the system, guys? If you remember vaguely, we had this problem a couple of times. It's just the area enclosed by this cycle, right? Because when you're going forward, you have the area under the curve as a positive value. And when you go backward, you sort of erase the bottom part of this area out. So you are left with just the positive area inside this cycle. And if you look carefully, what is the area of this inner portion here? Is just the width times the height. Okay. And because it's just the width times the height, it's P naught times V naught. And that is just pretty much perfect with what we got. We already got the results that the W is P naught V naught. Is the screen is slow? I think the internet is bad. There you go. All right, guys. I think you got that one. Okay, so once again, so the area enclosed is just the P naught times V naught, the width times the height. And that is exactly what we got here from the difference between the heat flow in and heat flow out. And that guarantees that we apply the first law of thermodynamics properly. Okay?
Okay.
Cool. Very nice. All right. So by knowing that this is what we are doing, actually, if you want to calculate the efficiency, it's going to be a simple task now, because the efficiency is what you get over what you have to provide. What you get is the work. What you have to provide is the Q hot. Yes. Or if you want, because now we have like, flooded with information, you can also pick the other expression for it. That's up to you. But now we know they are going to give you exact same value. Okay. So over here, I can just use work done as a P naught V naught. The Q hot is 13 over 2 P naught V naught. Once you cancel, you're going to get 2 over 13. And don't forget, the efficiency must be just a pure number. It cannot be that there will not be any units. There will not be anything. It's just going to be a pure number coming out of it.
Okay.
Okay, cool. All right. Not only that, if you sort of like look at this problem from the starting point and you really want to attack the final answer of the efficiency, actually you can cut your work in half, right? What I'm saying over here is, it turns out, because from the experience, once you have done this kind of problems many times, you can see that, well, Ajahn, because the heat 1, 2 is in, heat from 2 to 3 is in. When you go to 3 to 4 and 4 to 1, you're going to have an opposite direction of the heat for sure, because 3 to 4 and 4 to 1 is just the opposite process. Opposite means opposite direction process. That in comparison to what is going on in the first half of the cycle. Does that make sense? Right. So when you look at this one, it's like, okay, Q12, Q23 is in. I know for sure that Q34, Q41 must be out. So instead of going through the blue and the orange section over here, I don't need to. I can just stop from the first 2 segments and I just calculating the work done right away. Do you see what I'm trying to get to here? All right, just so, I just want you to think inside the sort of like the first law of thermodynamic mindset over here, that everything is conservation of energy. So that means when you look at this one, Ajahn, I'm okay with this, that Q12 is in, Q23 is also in, yeah. So I don't need to do anything anymore, because I can jump right ahead and calculate the work done, which is just the area enclosed, which is easy to calculate. It's just a rectangular region, P naught, V naught. So it means you're going to get this number right away. See that? So once you get that component of the W and you get the 2 components, the red and the green, you can calculate efficiency and then you are done.
Okay.
Okay. And from those 2, and then you can just figure out what should be the Q code. But this one works only when you don't care about the detail. Okay. And this probably go back to the question that your friend just asked as well. So it really depends on the information that you really want to gain from this process. If the information don't really ask you to calculate the fine detail of what's going on during each segment. So, just calculating the red, the green, and the yellow, you're done. You can figure out the efficiency already. However, if the questions like just sort of like dig deeper and like, hey, what is the heat flow during segment 3 and 4, 4 and 1, then it's too bad. You still need to apply the first law of thermodynamics anyway. Sounds like fun here, okay? And you are done with this, pretty much like the grand conclusion of what we are doing over here. Okay, does that help a bit? I hope. Sort of like, like this is a wrap for the first law of thermodynamics and its application in heat engine. Okay, all right. So make sure that you try a couple more in the homework problems, okay? Because there'll be a different type of PV diagram that you have to solve. So you're dealing with some other types of problems, I mean, other types of processes, and it's gonna be sort of like, tweak here, twist there. So no big deal. Everything has to work under the first law of thermodynamics. And I hope by this time you already knew it's just a conservation of energy. So you're doing the energy balancing of the system. Yeah, just transaction in and out, in and out. Okay. And then those transactions is in the form of either the heat or the work. All right, guys. So that's conclusion. So I think this is a good place to stop the first half of the lecture, because once we're done with this, after the break, I will show you the second law of thermodynamics. All right. But we are going to dive in just, so you have enough idea what the second law of thermodynamics is about. Okay. And I'll show you how to do a simple system calculations of the change of the parameter that we are going to talk the most in the second half, which is entropy. All right, it's going to be fun and confusing, I guess. All right, guys, so see you after the break. Okay, so what we have for you guys for the rest of the thermodynamics portion of the material is the entropy. I think you probably have heard this one many times at many places. All right. But anyway, the crux of this one is just it's about trying to explain something that the first law of thermodynamics is lacking. Seriously. All right. So we need this law because there is something else in the nature that's first law of thermodynamics cannot cover, even though everything has to follow the first law, but there is some extra things that the first law cannot reach. It's out of reach for the first law. So that's what we are trying to get to. All right. And see how it goes. Okay. So first thing first. Well, if I want to ask you what is entropy, that would be like the most boring question to start off anything, because it's so hard to answer. It's so broad, and then you don't know which point that you want to talk about. So let's just make a quick comparison, or at least link to something that you probably have heard of this word in relative to entropy all the time. Every time that people talk about the entropy, they talk about disorderness. Have you heard of this one? Disorder. Yeah, something is disordered, the disorder of the system. So what we are talking about entropy, I'm not so sure is this the good word for the entropy, but sounds like it at first. So let me explain. So what you think about is this. So what if you're trying to measure this? If the task is, all right, I'm going to show you what we're talking about in terms of the disorder of the system. Then let's do something simple. Let's say, consider just an isothermal process. Just make things simple. So the good thing about the isothermal process is you have a constant temperature process. So T will not change. The temperature won't change. And from the first law of thermodynamics, everything is good. The delta U equal to Q minus W. Delta U is gone. So the heat is just the same amount of work done. Cool. And you probably remember this. Let's use this one as the reminder that we did that before. And because the W is the integral P dV, and because it's a gas, so it's nRT over V. Yeah, and then because you have constant temperature, so nR and T can be pulled out from the integral on, and then you ended up with the nRT log of V final over V initial. This is what we did before. Okay. However, at this point, all right, we don't want to deal with that heat at like the whole heat flow or anything just yet. What we want to take a look at is just the change that happens at one instance of time. So I'm just going to take that Q equal to W and bring it down here. So from Q equal to W, now I would like to talk about just an infinitesimal change, right? So it's just like super tiny change. So think of it like if you're going to expand the gas, you're going to expand like just a tiny bit. So I'm just going to turn this into just a differential change of the work done by the system. All right. And then with that, I'm going to do the same thing with the Q, even though it doesn't sound, it might not make sense to some of you because dq is like change of the heat, That doesn't make sense. But I mean, at this point, this notation of the dq is representing that's a tiny amount of heat during this tiny amount of work that is being done by the system. Sounds okay?
Okay.
All right, just all right, take that as like a notation, all right, not like a differential change of the heat, because that will be kind of difficult to do. Because the heat is already the flow. So if you want to take the change of the flow, yeah, that's going to be like a second derivative or something. All right, don't worry about it. Okay, so what we're saying is just the heat during this tiny change. Okay, so the work is just going to be P dV. What is going on with my hands today? Okay, so the work is gonna be P dV without the integral, so you don't need to integrate. All right, just keep it as that. So you just take the pressure, multiply by the change in the volume in that instant. You can re-express P as the nRT over V just like before, so no big deal. Here comes the thing that we want to look at. I'm just gonna keep this dV by dt, okay? And I'm just gonna move the rest to the other side and pair with the dq. So what I'm getting over here is this equation there. The change in the volume relative to the original value of the volume, or you can think of it like a fractional change of the volume, is 1 over nr multiplied by this ratio here, dq over t. All right. So seems like on the right side, this is the only thing that has something to do with, state of the gas and all this stuff, and some sort of like a heat flow. The n is fixed, the r is just a constant, so there's no big deal. So this term looks very tempting that it might mean something to you. Okay, but what does it mean? If you really want to get the meaning of this, let's take a look at what we have on the left. So this one is the relative change of the volume. And imagine this. So this is my own analogy. I don't know if this one works or not, but just hear me out. So think of it like you have a playground and there are kids running around crazy, just playing this, playing that, on and on. And parents just sort of like waiting on the sidelines, just, maybe just, okay, just play a little bit and we'll just go home after this, on and on. But then suddenly the playground, the playground's area is just increased. So that means your kids can just run around even further away from you. I mean, you have more space for the kids to run. So things are getting more, out of hand because your parents going to get more worried because I don't know, where's my kids, on and on. So that's what it is. So increasing in space, it seems like you have more space for the system to be able to travel in there and then create more ways for the system to occupy. Does that make sense? So think about gas. If you have gas inside this, let's say this is the room that the gas is in, but then suddenly the volume of the room increases. So it means gas can travel further. I mean, there's more space for gas to occupy. So that means there are more ways that you can, fit the gas into this room. So that means the bigger the room, I mean, the volume of the room implies the more disorder. So I don't even know, like, is that a good word or not, but at least you can get an idea that, okay, there's, it's, all right, it's getting more crazier. You have more space to go crazy. So that's more crazy. So that's what it is. And that's implication there. Physicists interested in these terms right here. So this term gonna have a name, and that is the change in the entropy. Woohoo!
Okay.
All right. Okay, you have a question. Is that disorder? Okay, so the bigger the space, the more disorderness. Just stick with me for a little bit. But at this point, yes, bigger space mean more disorderness. But we're gonna have a better word for that toward the end of the class, I hope. All right, but even though disorderness seems to be all right, because you can feel that, yeah, you can, okay, yeah, more place to go. So, it's harder to find me because I have more place to go, something like that. Okay. All right. Now, what about the meaning of this change of the entropy? What's so good about this? So when you look at this one, it's just a ratio between the heat flow over temperature. This is the weird ratio that seems like the common sense doesn't sort of doesn't get to this because it's like Ajan, it's just an exchange of heat at one particular temperature. So what? Okay. So that's what it is. You probably have to look on the left-hand side of this thing. Okay. Because when you look on the left-hand side, the good thing about this one is the only parameter that you are dealing with is just the volume. And the good thing about the volume is it's sort of path independent, guys. Isn't that cool?
Okay.
Right? Because we sort of like, we like any variables that is path independent because just like energy, if it's here and you call this is your reference, you say, hey, energy is zero, gravitational potential is zero. If you leave it here, that's mgh. But you can just look away, look back, it's mgh. You can throw this mass out and then put it back here, it's still mgh. It's path independent. Same thing with the volume. From the look of it, it's like, okay, if volume is A and go change into B, you can just close your eyes, come back here and say, okay, it's B. So no matter what it is, it's a volume. So at least the good thing about this one is the entropy is path independence parameters or variables. So good. You can use it to describe the state of the system. So entropy is qualified to be a state variable. That's one good thing about it. Now, the problem with this, well, Ajahn, wait a second. You are dealing with the heat. Heat itself, it's path independent. I'm sorry, heat itself is path dependent. So what you're saying is, once you take the ratio of the heat flow with the temperature, are you going to get the entropy change right away? No, it's not that easy. Because if you do not specify the Q at all, Q can be anything, right? Because we said it's path dependent. You have to tell what to do. You have to tell like what kind of heats did you bring into the system, on and on. So at least you must have some sort of like a restriction of what kind of heats that you can involve in this calculation. And that's what it is. You need to take this heat that came from the reversible process only. Whoa. And we kind of like that because remember when we talked about the Carnot engine, we sort of talking about the reversible and irreversible process, and there is a heat involved in that process. It seems like every time you have an irreversible process, the heat during that process gone. Gone mean it's going to be useless. Okay, it's not going to be able to, bring it back and do something useful, or it cannot just take back and do something else to the system anymore. All right. However, on the other hand, if you look at the reversible process, the heat involved in that process is still sort of like, reversible, going back and forth. So it seems like heat is not lost forever to the system. Does that make sense, right? Remember that when we discussed the heat engine. So that's why we want that. We want the reversible heat. We want the heat that can be accounted for from the reversible process. All right? That's what it is. Just only this. Then you have the entropy defined properly. Okay, so conclusion, heat, even though in itself is not it's a path dependent parameter, but once you take the ratio with the temperature and you take the heat that comes from the reversible process, this ratio gives you a path independent parameters named entropy. Woohoo!
Okay.
All right. And there will be a big consequence of this, why we need the reversibility built into this. Because here we go. If you want a total change of the entropy, what do? Well, just integrate them. So you just collect the change and you just sum them up. Then the summation of something that's super, super, super small is just the integral. So that means, all right, you can always calculate the entropy change by doing the integral of the Q over T. No big deal. What's the deal with this is if you want to do it in a cycle, so it means if you have a cyclic process and you bring the system back to the original position, what do you expect? Yeah, there will be no entropy change.
Okay.
Just like, remember the U, the internal energy, it's another state variable. So it's a path independent parameter. So that means every time that you bring the system back to the original position, the U will not change. So the delta U is zero. Same thing over here. Okay.
Okay.
Nice. Okay, so good thing is S, the entropy is path independent. and it has something to do with the reversibility of the process. Okay, so it's like a fun fact. Actually, the name of this one, um, those physicists, I don't remember who exactly. Yeah, I have to look it up one more time. But anyway, he wanted to rhyme with the energy, and at first, he thought, "Oh, how come I forgot who's who?" It's gonna be pretty old, but it's somewhere around Kelvin or Celsius or who, one of those. Okay, I'll look it up one more time. Yeah, that's a good question. I didn't think of that before. Anyway, but the thing is, the entropy is supposed to be rhymed with the energy. And at first, they were thinking of the entropy maybe even as important as energy. But as you can see nowadays, we use energy everywhere, right? In pretty much all the contexts, like, and entropy is kind of like the concepts that's so hard to understand. So that doesn't make sense at first. But now, what is it? What is this entropy and why what it's so important? Okay, here we go. Once again, guys, come back to our beloved system that we have been looking at this a few times already. You have an insulated container, so there's no heat allowed to exchange. Yes. Now the container, it's fixed in volume, so you don't have any movable piston. You don't allow any volume to change. So that means there will be no work done in this system. So far, so good. So that means once you put in the gas at some initial temperature there, the temperature of the gas won't change because you don't have any transactions going on. So the delta U will be also zero. Remember this, all right? So this one, we have used this one to represent the isothermal process. But this one is the one that, okay, just like Ajahn, membranes just sort of breaks and gases fill up the whole space. Remember this one, right? We call this like a free expansion. Gas just expands twice as big as the original volume. So we can expect that if the initial pressure is P naught somehow, this pressure will just drop in half. That's no big deal, right? You still have equation of equation of state to carry on all the time for the ideal gas. P1 V1 over T1 equal to P2 V2 over T2. Right? All right, so that means when the volume is twice as big, the pressure has to drop down because the temperature stay fixed. So what is it? First law of thermodynamics is just say 0 equal to 0. You see where I'm going at here right now? So that means for this particular process, the first law of thermodynamics cannot tell you that. Everyone agree. Ajahn, this process that moving from left to right will have no way that you're going to turn this backward. This is impossible process. So everyone knows this process is an irreversible process. Yeah, agree? Yeah, well done. So that means the first law of thermodynamics cannot tell you the direction of change. Within the framework of the first law of thermodynamics alone, going backward is fine. It's not against conservation of energy because it's 0 equal to 0. I mean, 0 means no change. Total internal energy stays fixed. So you see the need for another law now?
Okay.
Right? So you need another law that at least can help you move along with like, okay, which is the direction of nature? And that's the second law of thermodynamics. All right, guys, cool. All right, so even though you might say, but John, wait a second, there might be a possibility that all the molecules in this container will just accidentally appear to be at the bottom half by accident. All right, but if you try to calculate using like probability, then you might have to wait like longer than the age of universe or something like that. Yeah, so that's not, let's call it impossible. Yeah, you cannot wait that long for, Avogadro numbers of molecules will just, collectively just, hey, let's gather around at the bottom half of this container. That's, you can say impossible. All right, so that's, I think that is a scenario that's qualified for impossibility here. Okay, all right, so that's it. So what can we do then? Let's calculate the change in the entropy and see how it goes. So at least you got some sort of like, a clue that, oh, okay, so the entropy change might have something to do with this. Okay, so how can we calculate this, guys? Here we go. So let me start off with this question. So I'm going to have the PV diagram once again. We love PV diagram. Okay. And if I want to call this process to be like process number one, okay, let me call it, or I mean, I can call it A. I just use 1 and 2, but then the next slide is like A and B. So I don't remember which notation I used. Okay. So over here, I have A and B, which I can point sort of like, put a point in a PV diagram. So let's say point A is the volume is going to be, let's call that V. The pressure is P naught. But then point B, you increase the volume to twice as big. And we know that the pressure are going to drop in half. Cool, no problem. Here comes the question. Write down the curve in the PV diagram that describe this free expansion process. Oh, this is maybe annoying. You don't have any sort of, you might not have like concentration to think or John, that annoys me. Okay, what kind of curve that can connect between the point A, the initial position, and point B, the final state of the system? What do you think? Just come to think of it, Ajahn, temperature is constant. Yeah. And you told us all the time that every time that we have a PV diagram, it's sort of like a beneficial that if you imagine that there is an isothermal line passing all the points all the time, right? So that's kind of thing that we sort of like discuss and use all the time. So Ajahn, I'm gonna take it. It's gonna be isothermal process here. There you go. Bam, right there. What do you think? Agree or not?
No. Okay.
Agree. All right, very good. Agree. What about everybody else? Okay. So this is sort of like I'm it's gonna be a trick or something. Some of you are gonna think about that. Okay, the problem is this. The answer is not quite. Because let me erase this one first. Because think about this. Right at the moment that the membrane breaks, gas start to fill in the void, start to get into the vacuum, right? During this process, if I'm standing right here, woohoo, at the upper left corner, I'm still in the vacuum. And if another person just waiting next to the point of whatever the hole or whatever the breaking point, they will feel like, oh, the pressure is so high. And it's not going to be like a static pressure because something is going to blow, that person right now in their face and everything. So you're going to have to use like Bernoulli equation on and on.
Okay.
No, there's no need to grab that. But that's what it is. So what I'm saying over here is this process right here, the expansion thing is sort of like remember this word? Quasi-static here. So that's why I would like to talk about this. So this process is too quick. Okay. The thing is going on so quickly that you don't have enough time to make the system rest and get into equilibrium. And then you just measure the parameters nicely. There's no single value of the pressure during the process. There's no single temperature during the process because up here, I'm still in the vacuum. So, all right, if you don't mind, the third law of thermodynamics, I'm going to say I have nothing. It's a 0K, but it doesn't mean 0K in like a reality or anything, but it's 0K means I'm in a vacuum. I don't have anything to measure. Okay. So what I'm saying over here is it turns out there's no way on a PV diagram that you can draw any particular line. It's sort of like a blur is like a blur. I don't know. Who knows? So that means when you cannot draw any line in a PV diagram, so it means there's nothing that you can deal with this properly using the PV diagram. But doesn't mean that the gas does not happen, but at least it's not happening in a quasi-static manner. So that's why you cannot draw the diagram nicely because you don't know how to measure all those points. Does that make sense now?
Okay.
Okay. But don't worry. Even though, right, your answer has a very good merit of being a good process to track this whole thing. Why? Hey guys, S is
Okay.
path independence. So connecting these 2 points using isothermal process seem to be a very wise choice because we know how to treat this line. You guys with me now? So my conclusion about the first step over here is I'm going to take it. I am going to take the isothermal process to me the process that connecting between A and B, even though it's not a real process that is going on. But this is going to be a process that I can use to calculate the delta S. Woohoo!
Okay.
Okay, let's go for it, guys. So how can we calculate this delta S? Everyone knows how to do this because everyone knows how to do the isothermal process calculation. So let's attack this one. Okay, guys. So let me redo it one more time so we can sort of like, build understanding together, even though everything is already on the slide here. So isothermal process, delta U is 0. So the heat is W. Yes. So far so good. And as we agree, we're going to talk about things that changing infinitesimally step, like super small stuff. So we're going to call it dq equal to dw. And the dw is just p dv. Yeah. So far so good. All right. We're going to eventually do the integral soon, but that's what it is. So what you can do is you are changing the entropy. It's just the ratio between the heat flow over temperature. So what you can do is you just take the dq divided by T. So I just divide through by temperature for the whole thing. It's no big deal. All right. Now, P equal to nRT over V, just like before. So it's nRT over V. I have extra T down here. So far, so good. So now your temperature cancel. All right. So now your temperature is out of the picture. Then now your turn to do the summation. So I'm going to sum them all from A to B. At the end, you're going to get the total change of the entropy from A to B. It looks good. All right, next, everyone knows how to integrate this. N is constant, R is constant. So all you need to do is just integrate 1 over V dV, just like before. You end up with the log of the V going from volume at A to volume at B. All right, now, when you look at that, well, John, the volume is twice as big. Okay, so once you substitute 2V and the V for the limits of integration, you end up with NR log 2 right here, and you are done.
Okay.
Cool. See, so this is how you calculate the entropy change by grab any path. When I say any path, because the change in the entropy is path independent. So that means I can do this too if you want. Why not? Or I can just drag a straight line if I want to, or I can do this, or I can curve and come down here if I want to, if I'm crazy enough. But the whole thing is no matter which path you take, it just maybe give you more complex, I mean, more complicated way of calculating those delta S. Okay. However, at the end, once you're done, you're going to get exactly the same in R log 2 altogether. All right. Is that cool?
Okay.
So that's just a good thing about the entropy. It's path independent. So you can drag any path that you like and use that as a tool to calculate the change of the entropy. Okay. And of course, we already picked a good one. The isothermal process is a very perfect one that we can calculate change in entropy very, very straightforwardly. Okay. All right. So there's a question here. So entropy also increases in an, oh, very good.
Okay.
Very good. That's what it is. All right. So you sort of get an idea we are trying to get to. See this? The delta S that you're having over here is positive, guys. It is positive. So that is the indicator saying that the process that we are looking at from left to right. Okay, I don't need new arrow here. This is the process that is irreversible.
Okay.
Yes, exactly right. Why? Because the only way that you're going to have something that is reversible, delta S must be 0. That's the whole thing. The reason is when you keep the S to be at the same amount, okay, that means no change. So you expect that there is no reversible heat is going on at all. So it's like, okay, no matter what you do the transaction, at least you come back to the original position. And because we only take care of the reversible heat, we're not losing anything, right? Because we are not losing any heat to something else. It's still the heat that is still running around in the system. So that means if you go whatever, do the transaction and then you come back to the original position, at least the heat that you require is going to be the same as the heat that you have to, deposit back on and on. And that is the signature of reversible process. Whatever you do, if there's no entropy change, that means you are still reversible. But at the end, if you calculate the entropy change and it turns out there is non-zero problem. I mean, there's non-zero process going on. So that means you already do something. There must be some changes going on, and there is an sort of like imbalance between exchanging that you have, you're trying to do. And that exchanging of the stuff seems like to give you to some point that is still not yet reversing, because you have a net change in the entropy. So you are sort of like you're going forward. And that's something that is not reversible at this point. Okay. So you're probably wondering about John. So if it's it's just like so entropy can decrease. The answer is depending on what you are looking at. If you're looking at just a small portion of the system, yes, that portion might be decreasing. But if you take into account everything, what I'm saying everything is this. Look at this, guys. If you look at this gas here, the gas is being contained within this container. Yeah, let me sort of draw the line over here. So the gas is within this boundary over here. And then we do not allow heat to exchange, do not allow work to do. So that means this system over here is already disconnect to the rest of the universe. Wow. All right.
Okay.
So it means there's no interaction with the environments anymore because you don't allow any heat to exchange. You don't allow any work to do heat to exchange. Right. You do not allow any heat to transfer. You do not allow gas to perform any work. So it means there's no way that you can transfer energy in or out. So this is it. So we call this an isolated system. So as long as you have an isolated system and turns out you got a positive change in the entropy. You got that idea now? Because you do not allow any heat to exchange. So in general, you would expect that the system is supposed to stay quiet, don't do anything. So you shouldn't be anything going on in there because we don't have any exchange whatsoever. But somehow when we calculate the entropy turns out to be positive. So that means something in that system must be changing in the direction that is not reversible. And it's sort of hidden from the first law of thermodynamics. Does that make sense?
Okay.
And that's the reversibility. So in this case, you can see now the entropy is positive. The positive entropy change of an isolated system indicates the irreversible process. And that's the conclusion why this expansion of the gas in this tank is an irreversible process. Because no, it's an isolated system. You cannot have a negative entropy. Woohoo!
Okay.
Okay, so this is the grand conclusion. The best that it can do is entropy can remain constant. That is the best that it can do. So delta S is 0. Or it has to be definitely increasing so that delta S is greater than 0. So in conclusion, to answer to your question, yeah, that's the weirdest thing. delta S of your universe. When I say universe, doesn't need to be like a real universe, but it means your system of your consideration that is already your universe right here. This is my universe here. It's mean isolated system, right? So when the delta S of the everything taken into account, this is it. The second law of thermodynamics says it has to be non-zero at all times. Isn't that amazing? Okay.
Okay.
And that's the conclusion that we put in sentence over here. The change in entropy of the universe must be greater than zero for irreversible process. So once you have an isolated system or you have your whole universe in your hands and you calculate the entropy change and it's positive, something irreversible is going on in there. The best that you can do is just keep it at zero and the process that in there is still reversible. Isn't that amazing? And that's sort of go really well with what you have. You are growing and you are getting old. And that is an irreversible process. So that means you have an increase in entropy. The best that you can do is you keep your entropy to be zero. That means you stay as still as possible. So, I mean, you cannot get any younger. Okay? Your cell is going to be dissipated, dying. We're gonna sort of, turn into turn into ashes, and then everything. We're gonna die, be part of the particle in the universe, on and on. So that's what I'm saying. Is eventually, what you get is you going. We not you. I mean, I'm included. We are going to the end of the universe. So now we talk about real universe now. So the universe right now is sort of expanding and everything. So we, as of us, is in the universe that is increasing in entropy. So eventually the entropy will keep increasing until at the end of time. That's when the entropy will not change anymore, but that will be at the maximum possible value of the entropy. So here comes down to the question. So what does the entropy really mean? Even though if you want to use the word disorder, to me, it's yes and no. All right. So think about this. When you have like a new desk, okay, you have like a desk. When you bought it new, it's clean. But now later you put your laptop there, you start to put the books here, stationery there, on and on. It's get clustered, get chaotic on the table. So that is the increase in entropy. Make sense? Because the disorderness is going on. You have a piece of paper here, a piece of paper there, on and on. But then you can decrease the entropy by put some work into it. Okay, put them in order. Stuff here, throw this away, make it clean again. So that portion over there, you're decreasing the entropy because things get more order on your desk. Does that make sense? However, to do that, you have to spend something, and you have to work on it, flex your muscle, burn some food, turn some energy into something that you can lift the paper, throw it away. The paper that you throw away, make some crazy stuff at the trash, say you increase the entropy at some other point. You decrease your entropy on the desk, but you increase your entropy in your body and in the trash. Does that make sense? So if you take into account everything, eventually if it's a reversible process, okay, the whole thing is still, stay at the same entropy level, but you expect that when you throw some paper away, your body is getting older, is irreversible. So if you take into account everything to be your universe, then the total change of the entropy is increasing. Whoa, isn't that amazing? All right.
Okay.
So that's what this second law of thermodynamics is about. It's about the reversibility. But then think about it. Maybe disorderness might not be the good word because of this. Think of the end of the universe. And I would like to quote this one just for you to think along with it. It's the end of time. Why? Once your universe keep expanding, you guys getting older, everything just going, dissipating, disappear, or decimated, or whatever, things get destroyed. It's gonna get broken. Everything gonna be done and down. Everything just come down to nothing. that's the end of your universe. But you think about it, at that the end of time, actually the universe is already at the most ordered. Does that make
Okay.
sense? Because there's no place in the universe that you can do anything anymore. There's no heat flow because everything is so uniform. Everything just so uniformly distributed across the universe. So that's a very peaceful time because that is the end of time. Nothing changes anymore. So that's why disorderness may work or may not work, depends on the context that you're trying to talk about. But just for the purpose of the course, yeah, disorder is kind of all right. Okay. But to me, think of it like it's the way that the system can sort of like spread around. If you have more ways that you can spread things around, okay, then that is sort of like, okay, you have more ways. So that's implied disorderness. But when you don't have any choices, this is it. You have only single choice. That's one choice. That's when you don't have any choices. That seems to be ordered. So it seems like it depends on the number of configuration. Configuration means the way that you can arrange the system. The more of the configurations you can access to, that means you have more stuff, more stuff in your system. When you don't have any choices, you only have like, I'm gonna have to take this, no choices. That's when you have less stuff. So that's mean more ordered. So just to make connections with this. So think about this. So this system turns out, you can see that you can think of this one like this. Up top, there's no gas, you can call it zero. Once a portion in the top has gas, you can call it the one state. See this? So you can call the left side to be the state zero. You can call the right side to be the state one. So that means this system of gas over here can be used to store information.
Okay.
Does that make sense? And that is the, there's a zero and one. So it's like a one, it's a bit system over here. Does that make sense? So what you have over here is a one bit system. You have a choice between yes or no, zero and one. And that's number two is going on here. It's 2 to 1 right there. Okay. So it turns out for those of you that eventually will do the data science people or data engineering, computer science, computer engineering, everything, eventually you will have a chance to quantify the amount of information like, you do the data and all this stuff under the concepts of entropy. So when the number of this one is bigger, that means you can store more information into it. But when you have more information into it, means that system must have more arrangement for you to be able to play with. So that's why entropy links directly to the amount of data that you can store in that system. All right. For us in this system, it's so simple. The information is so simple. It's only yes or no. So that's why you only have two choices here. Cool.
Okay.
All right. And that gives you a conclusion of the second law of thermodynamics that's enhanced. Of course, it's enhanced and actually take into account the things that the first law cannot do. The first law only conservation of energy. The second law, the entropy, tells you the directions of the change that is happening in nature. Cool. All right. There's a question. Who came up with the law?
Okay.
A couple of people. One person you probably have known him already, the Lord Kelvin, the one that you use in the unit, the absolute temperature units, and maybe the big person that works into this, like the entropy stuff and the pure thermodynamics, is the Boltzmann. You remember Boltzmann, the one that we have a Boltzmann constant in PV equal to KNT, yeah, NKT, yeah, that Boltzmann constant. Boltzmann is the one who actually pioneered this, and there'll be a couple more people, Celsius, Helmholtz, and Kelvin, yeah, some those people right there. It's a lot of fun. All right. I'm just curious, when the sun expands, it does no work, right? Because around is just vacuum. All right, here we go. Um, that's well, once again, it depends on the system, right? When we study system all the time, you have to draw the line. What is the boundary of your system? So what you're seeing over here is, even though you say you push the vacuum, but if you take into account the whole universe to be your system, the expansion of the sun take up more volume of the universe. Does that make sense? Right. So that means you have less space for the rest of the universe to travel because the sun is started blocking. So even though it seems like you're not doing the actual work, but it has some effect onto the rest of the universe, given that the universe is in reality not a pure vacuum. However, if it is a real vacuum, that's another story because you have nothing else to interact with. So the concept of work is already disappeared since the beginning. Does that make sense? All right. So in general, the rest of the universe still have some other stars. You have some particles running around. You know, you have some electromagnetic waves blasting through back and forth, on and on. So it turns out sun is still interacting with the rest of the universe. So I would say it's not nothing. It has something to do, even though it could be tiny, tiny. Is universe an isolated system? I hope so. Oh, no need to clap there. Because we don't really know the age of the universe, even though we, from the experiment and everything, we know that our universe is expanding, but we don't really actually can say certainly that there are no other universes going on. The multiverse is happening in the Marvel. No, no, just kidding. But it means we only see so far as our experiments, you know, our whoever people that's looking at the sky is looking at. So yeah, at this point, probably isolated up to the edge of the universe. But do we have other universe nearby? Who knows? Yeah. And we're still having like some theory talking about the big crunch and everything. So even though right now it's like there was a big bang and it seems to be an acceptable theory explaining what is going on, but then they're still thinking that there might probably, I mean, there's possibility that things are going on in oscillation. So it's like a bang, and once it reaches the end, or maybe it's not the end of time, just like what we're seeing over here, there might be a time that it turns out the gravitational field seems to wins out everything that's going on in the universe, and it sort of start to move things, you know, back together, and then everything's just contracting down. I don't know, is that possible or not? But or I don't know, is that winning or losing? But the idea, it could be like an oscillation of a bang and a crunch and a bang and a crunch, and each time we have to wait like a billion of years to see that. So who knows? All right, but at the moment, yeah, universe, I mean, the actual universe of us is expanding, and we're expecting the end of the universe sometime, someday, some billion years from now. Thank you. All right, guys. Any questions so far? All right. Yeah, I hope you learned something today. All right. But anyway, don't worry too much about the complicated problems in this. I only have like an okay question that you can put some thought into it, and you should be able to arrive at the final solution. I mean, final answers. All right. Just check out the homework set 4, and that is just for the entropy part. All right. Just basic stuff like you mixing this and mixing that, and then just calculate the entropy change just to confirm that every time that the entropy change is positive in an isolated system, that process that you're looking at is irreversible. Okay.
Okay.
Might have an existential crisis. What is that? Existential crisis. What does that mean? What is this word means? Like what? What does this word mean? Existential crisis. All right. I don't know. Do I have to look it up, or kind of like depression? All right. No, about this course, all right, don't be. All right, just sort of like, you know, enjoy what is going on around us. Okay, guys. So I hope you learned something about nature, all right, and don't be so depressed about this. See, you think too much now. All right, just stick with it. stick with what we have right now, right? Don't worry about the end of universe at this point. All right, guys. All right. Thank you so much for today's. And then I'll see you guys next week. All right. I will put the poll for the exam dates soon. All right. And then you guys can interact through the Google Classroom or Line group. Okay. All right, guys. Take care. Stay safe. I'll see you guys next week. Bye bye.
Okay.
Thank you.
When I feel the autumn breeze, I get way too bittersweet. Thinking about you, thinking about you. And when I see the autumn leaves dancing through the swaying trees, thinking about you, thinking about you. I hit you up, we were good. We were talking and I honestly felt chemistry, but it seems like things were meant to be. You and me, always drifting away separately, yeah. But I really know, yeah, I know that we're different. Chasing different things, never listening. Never really knew what I was missing. All these little lies I was living. Spaces in between us, traces of our memories won't change as I see in us. Always seem to be knowing that when I feel the autumn breeze, I get way too bittersweet. Thinking about you, thinking about you. And when I see the autumn leaves dancing through the swaying trees, thinking about you, thinking about you. Hope you'll find somebody new. I never really knew how much it meant to me, but now it's plain to see. Know that you've been fed up, you deserve much better. Never meant to pressure you. I know you couldn't handle all the pressure, and I try my best to hold myself together, but I guess that we were meant to last forever. Last forever. Spaces in between us, traces of our memories won't change as I see in us. Always seem to be knowing that spaces in between us, traces of our memories changes I see in us. Always seem to be knowing that when I feel the autumn breeze, I get way too bittersweet. Thinking about you, thinking about you. And when I see the autumn leaves dancing through the swaying trees, thinking about you, thinking about you.